Hello, so for this tutorial, I'm going to be going over calculating sequence identity of a pairwise alignment. We're going to calculate positive identity of a pairwise alignment. We're going to calculate alignment score. We're also going to write a regular expression of a given multiple sequence alignment. We're going to globally align and locally align two given sequences. Identify an unknown protein sequence using NCBI BLAST, and find ribosomal RNA of an organism using NCBI database. So first we're going to calculate sequence identity using method 1 of this pairwise alignment. So first you can just look at the formula here, and we're going to take the total length of the shorter sequence, and then we're going to take the number of aligned identical sequences and take the number of aligned identical sequences and divide by the total length of the shorter sequence. So first we just need to count the matches. We have 1, 2, 3, so 3 matches. So that would be right here as the numerator, and the denominator would be the shorter sequence, which is going to be the bottom one, which is going to be 6. Divide that, times it by 100, and we'll get the sequence identity, which is 50%. Second question is asking for you to use the second method, so method 2. This time you're going to take into account the shorter sequence and the longer sequence, so both sequences. Count the lengths, add them up together, and then find the number of matches and times that by 2, and then take that number as the numerator and divide by the total length of both sequences, multiply that by 100, and you'll get the sequence identity. So first we'll just count the number of matches, so 1, 2, 3, so it's 3. Times that by 2, because we're going to include both sequences, which the bottom sequence is 6 and the top sequence is 8. So we're going to divide that out, multiply by 100, and we get 43%. So that's method 1 and method 2, and you had the formulas right here. Just remember, for sequence 2 or method 2, you're going to be taking into account both lengths of the sequences, and then method 1, you're only going to look at the shorter sequence. Okay, so for part 3, question 3, we're going to use the Blossom 62 matrix to calculate positive identity percentage for the alignment. In this case, we're going to be aligning two proteins. So we have protein sequences, and then we're aligning the amino acids within the protein sequence. And we're going to use the Blossom matrix, and we're going to be using method 1 and method 2, which is similar to sequence identity, but we're using the Blossom matrix in this case. So to get the percent identity for method 1, we're just going to first just look at the identical matches. So 1, 2, 3, 4. So we have 4 matches. Then we're going to look at what appear to be mismatches, but we're going to use the Blossom matrix to determine whether they're actually going to be a match or not. So to do that, we can take T, we can take L, and we get -1. So this would be a mismatch. Anything greater than 0 would be counted as a match. Anything less or equal to 0 would be a mismatch. So T and L is -1. So that's going to be a mismatch. And we look at what appears to be another mismatch, but we're going to verify whether it's going to be counted as a match or a mismatch using the Blossom matrix. So we look at E and look at V, so we get -2 right here. So that's going to be a mismatch as well. We're not going to count that. Q and S, we can take S, Q, so this would be 0. So that's going to be a mismatch as well. And then we have S, and we have M, S, M, right here, -1, that's going to be counted as a mismatch. So we only have 4 matches. Divide that by 10, which is the shorter sequence right here, and we'll get 40%. And then we can do the same thing for method 2, but we're going to take into consideration both lengths of the sequences. So the top sequence is 10, bottom sequence is 11. Add them up together, get 21. Our numerator will be just the matches that we counted up, times that by 2, and we'll get 38%. So just remember, with using a Blossom matrix, you're going to refer to the Blossom matrix to figure out whether what appears to be a mismatch, we're going to verify whether it will count it as a mismatch or not by using the Blossom matrix. Figure out whether T and L have a positive or negative number or zero. If it's zero or negative, it's going to be a mismatch. So this would be a mismatch. If it was positive, we don't have a positive here, but if it was 1, then we would count it as a match. Okay, calculating gap penalty. So all we're going to do is we're going to look at the scores they give us. So this is opening penalty, and this is the extension penalty. So this right here is an opening penalty. So we're going to put that as -5 right here. This right here is another opening penalty because it's occurring on the bottom sequence and not the top sequence. This is a separate opening. This is a separate opening here as well. But we're having an extension occurring right here after this gap opening. So -1, another extension, -1, and then we have an alignment, and then we have another opening on the bottom, on the top, so that's going to be -5, and we have extension at the bottom, at the top right here. So gap opening, and then extension, extension, another gap opening, and then extension. So we'll just add these up together and get -18. And at the question 5, similar, but we're also going to include match scores and mismatch scores. So in this case, we just look at the matches. So V, V, so we'll put a 1 there, A, 1 there, those are matches. And then it's a mismatch, -1, and I believe that's it. And then we just start looking at the gap openings and gap extension penalty. So right here is a gap opening. And then here's a separate gap opening over here at the bottom sequence, and then a gap extension, and then another gap opening at the top, and then a gap extension. Then we can just add up all the scores. So we had 2 matches here and here. Multiply that by 1, which is the score, and we get 2. We only have 1 mismatch, and the constant and the mismatch score is -1. So multiply that by -1. Then we get the gap openings, 1, 2, 3, times that by 3, get 15, -15, and then gap extensions. We look at here, we have 1, 2, 3. Multiply that by -1 and get -3. Add them all up together, and we get -17 for our alignment score. Next, we're going to be using the Needleman-Winch and Smith-Waterman algorithm, global and local alignment, on these sequences right here. So first, let's open this up. I'm just going to copy and paste it into my browser. Okay, so let's see what the first question is asking. It's asking to perform a global alignment. So we're going to do the Needleman-Winch algorithm. We can take sequence 1, copy, paste, change this to DNA. Sequence 2, copy and paste. And just want to run default settings. Click submit. Once we get our results back, we'll figure out what zone it's in. Okay, so 94% with identity and similarity makes sense because it's DNA. We're not using Blossom matrix. So here we have our sequence identity. It's above 35%, so it's going to be in the safe zone. Next, we can look at 2 other sequences here, but this time we're going to globally align them. Notice how sequence 1 is significantly, or appears visually, to be longer than sequence 2. Okay? Just take note of that when we are performing a local alignment. Okay, so we're going to switch over to the local alignment. Sequence 1, copy, paste, let me make sure that this is the sequence I'm getting. Copy, paste. There we go. Okay, and then sequence 2. Okay, and then now we can simply submit. Once we get our results back using the Smith-Waterman algorithm, we can find out what our score will be and what zone we will have. So here it's between 20 and 35%, so it's going to be in the twilight zone. And you can see that the Smith-Waterman algorithm is trying to align different local areas within the sequences. Well, within the longer sequence. Here at the top, longer sequence. At the bottom is a shorter sequence, and you see that the shorter sequence has some local areas that are being aligned within the longer sequence. Okay, but this will be twilight zone, in between 20 and 35%. Okay, question 8 is asking, it's giving us 2 different lengths, sequence lengths, and asking what alignment should we perform. Well, in this case, the lengths are really similar. Okay, there's only a 78 base pair difference. So we're going to globally align the sequences. Now, if this was, just say if it was like maybe a 4,000 or even shorter, 2,000, then probably want to do a local alignment. Okay, next, question 9, we're given this protein sequence, and we're going to first identify the protein name, gene name, and organism source, and then we're going to find the RNA sequence of that organism. Okay, so we're going to copy and paste this into NCBI Blast. You can just type into your web browser, search box, just type in NCBI, open up the Blast page, the Blast suite. Make sure you're on Blast P, because we're going to be inputting a protein sequence, and I'm going to use Quick Blast and just use the non-redundant protein database, protein sequence database, and just run Blast. And then our top result, we're going to just focus on the top result and then use that to answer the question. So here it is, E value is really low, percent identity is high, so we're going to click on the accession number. Okay, and then you can find the organism source here. You can also go down and look at the gene, but at this point I'm just going to click on the database source. I'm going to click on the accession number for that database, which is UniProt KB, and we're going to have the protein name, which is Moricin 1. Then we have the gene name, MOR1, and then we have the organism source, silk moth. Next, it says now obtain a RNA sequence of the organism, so ribosomal RNA. So we can actually go back one from UniProt KB, and then we can just click on the organism source right here at the bottom. Then we can click on nucleotide, where it says the Entrez records, database name, nucleotide, direct links, click on nucleotide, and then we can, let me just clear this real quick, on where it says molecular types, just click on ribosomal RNA, rRNA. If you don't see it, just click on customize, and then you should be able to see what you can filter by. Okay, so here, here's the answer, so we can now obtain an RNA sequence. Now notice it doesn't ask a particular ribosomal RNA sequence, it's just now obtain a ribosomal RNA sequence. So any of these would do, so you can click on the first one if you like, and you can snip it or copy and paste it as your answer. Okay, next. Okay, so with question 10, We're going to be creating a regular expression with this multiple sequence alignment. So regular expression represents a pattern. These patterns are denoted as a sequence of characters. So in the question below, we're basically going to take this multiple sequence alignment and represent it as a regular expression. Okay, so notice how in this multiple sequence alignment, each row is a sequence. Okay, this could be protein sequence 1, protein sequence 2, protein sequence 3, all the way down to the nth protein sequence. And then each column represents the position in that sequence. So this is the first sequence, this is the first amino acid in the sequence, second amino acid, third, fourth, fifth, all the way to the 12th, or however long your multiple sequence alignment is. We're going to be using regular expression symbols, so these patterns, to represent this multiple sequence alignment. In this particular question, we're going to assume that if it's more than 3 amino acids in each position, it's going to be any amino acid can occur there. And on the 12th position, it can never be an A, okay, alanine. So let's start off with the first position, so looking at 1. So here, there's more than 3 amino acids, so we're going to put an X to represent that any amino acid can occur in position 1. Next, we're going to look at position 2, which there's only going to be one, so it's going to be just a W. Only one type of amino acid here, so we're going to put a W there. Then, in the third position, we have valine and isoleucine. So, in this case, we're going to say that it's slightly conserved with valine and then one isoleucine. So, we're going to put brackets, and within those brackets, we'll put valine or isoleucine. And this brackets is saying, at position 2, it can either be a valine or an isoleucine. Position 4, it's the same thing, valine, but a leucine. So we'll put in brackets, valine or isoleucine. So at position 4, it can be a valine or leucine. Then going on to position 5, we have T and S. At this point, it can either be a T or an S. So put this in brackets, T or an S. And then position 6 or 7, notice how these both have the same amino acid, alanine, alanine. So as a regular expression, we can put an A at position 6, but then we can say for these two positions, so this is 5, and the next two positions are going to be an A. So 5, 6, 7, and we move on to the 8th position, which is going to be a histidine. So look at the 8th position. This is a histidine. So we would put an H right here. Notice how we're separating each position with a dash. Next, we have the 9th position, which is cysteine and valine. So we're going to put cysteine or valine and within brackets because it could either be one or the other. And then for position 10, we have 1, 2, 3, 4 different amino acids. So that means we're going to, because of the rules that are given, that we're constrained by 3 different amino acids, means it could be any amino acid occurring in that position. So regular expression will contain an X for position, 10? And then 11, we have exactly 3. So in this case, it's not more than 3, so we're going to put E, D, P can occur in position 11. Okay, remember putting in brackets because it can be either E, D, or P. The 12th position can be anything except for A. It can never be A. So we're going to use the curly braces to denote that this could be anything except for A. And that's our regular expression. Next, given the sequence, this sequence right here, and the following pattern, does the sequence fit the pattern? Explain why or why not. So let's just look at it. So this position 1 can either be, in this pattern, position 1 can either be an H or an S, which is good because there's an H there. Position 2 can only be an S, so that follows. Position 3 can be a T, that follows. Position 4, this right here, does not look like it can follow. It says that this pattern needs to be a histidine or an H or a T, but it's a K. So right here, our pattern has, the sequence does not fit our pattern. But let's continue on. A, good. This can be any amino acid, any amino acid, any amino acid for the 4 sequences. Any amino acid, any amino acid. So at this position, it could be any amino acid for the next 4 sequences, 4 positions. This one, it can't be G, H, or a V. Well, this appears to be a G, so this is already out. Then we have an S. Good. We have an M or a T, that's good. V, good. H, good. V, good. SM, nope. This is not going to work because this is going to be an H or an M, but here we have an S, so this pattern does not fit the sequence. H, good, and this can never be an M, but the sequence is an M, so this doesn't fit. Okay, so we have 1, 2, 3, 4 reasons why this sequence does not fit the pattern. Okay, notice how I just went from each position, lined them up, and determined whether it fit the pattern or not. Just reading it off. And that's how you're going to answer a question like this. And that's the end of this tutorial.